You know those vector problems that just look tricky? Well, today we're going to take one apart, a real GCSE question, and show you that it's all about following a few logical steps. By the end of this, you'll see exactly how to tackle these. Let's jump in.
Okay, so here's the one we're looking at. This is question 15 from the November 2024 higher tier paper. You can see we've got a parallelogram, some ratios, and of course, vectors. We're going to break this down step by step.
So, first things first, what are we actually trying to do here? The whole point of the question is to find the ratio between the length of the vector xn and the length of the vector mn. That's our goal. Before we can even think about calculating anything, we have to pull out all the information the question gives us. All the clues are right there in the diagram and the text. Let's start with our first building block. We're told that the journey from point O to point Y is represented by the vector A. That's our first fundamental path. And just like that, we have our second one. The vector B takes us from O to Z. These two, A and B, are basically the foundations for everything else we're about to do. Now here's where the shape becomes really useful. Because this is a parallelogram, there's a neat shortcut. To get from O all the way to the opposite corner X, you can just add the two side vectors together. So OX is simply A plus B. The question also tells us about these 2 points, M and N. We're given ratios. M splits the line OY into a 1:3 ratio, which means it's a quarter of the way along. So the vector OM is just 1/4 of A. Same logic for N. It splits OZ 1:2, so it's a third of the way along, making ON 1/3 of B. Easy enough. All right, we've got all our pieces on the board. Let's make our first move and figure out the vector that takes us from M to N.
So how do we get from M to N? Well, we don't have a direct road, do we? But that's okay. We can just create a path using the routes we do know. Think of it as a detour. Now, according to the mark scheme, this is the answer we're aiming for. That O just means or equivalent, so any other way of writing it is fine too. Let's see how we get there.
So our path is going to be from M back to the origin O, and then from O up to N. The journey from M to O is just the reverse of O to M, so it's -1/4 A. And we already know O to N is 1/3 of B. Put them together, and there you have it. Mn is -1/4 A plus 1/3 of B. Perfect. Okay, one down, one to go. Now we need to find the vector for xn, and you'll see it's pretty much the exact same process.
Right, so what path can we take this time? How do we get from point X all the way over to point N using our known vectors?
The mark scheme points us towards a specific route. Let's travel from X back to O, and then from O up to N. Let's follow that path and see what we get. Okay, so going from X to O is the opposite of our diagonal vector, so that's -A plus B. Then we add the vector for ON, which we know is 1/3 of B. Now we just need to tidy it up. We get -A and then -B plus 1/3 of B, which gives us -2/3 of B. And there's our vector for xn. So that was the heavy lifting. We've got both vectors we need. Now it's time for the payoff. Let's put it all together and find that final ratio. So here they are, our two calculated vectors. Now just take a second and look at them. Do you see a relationship? Notice how the components of xn look familiar compared to mn? We're on the home stretch now. Once you have these two expressions, you've pretty much cracked it. If you look closely, you can see that xn is exactly 4 times the vector mn. Try it. Multiply mn by 4 and you get xn. And that's it. That's our answer. Because the vector xn is 4 times the vector mn, it means they're parallel, and the ratio of their lengths is simply 4:1. Job done. So let's just quickly recap what we did there. We used ratios to find points on a line. We used that handy parallelogram rule. We found vectors by creating a path between 2 points. And finally, we simplified our expressions. These are really the core skills for vector geometry. So, to leave you with a little challenge, how could you use these very same ideas, especially that part about one vector being a multiple of another, to prove that 3 different points are collinear, that they all lie on the exact same straight line? Something to think about.